Our speaker of today is Anat Canning. Anat completed her PhD in geophysics in Rice University in Houston, Texas. And she is working at Paradigm as R&D manager for seismic reservoir characterization. Anat is teaching condensed courses for the oil and gas industry worldwide from 1995. And the research interests are seismic reservoir characterization and unconventional oil and gas seismic exploration. Please.
Thank you. Thank you. It's very exciting to be here. I was asked to give this in English, so please feel free to ask me questions as we go along. So I wasn't really sure what is the background of the people, so I try to make it as simple as possible. So I hope it's on the right level. So the topic of my talk is how to use the seismic data for unconventional oil and gas exploration. So I hope everybody knows what is seismic data. Yes? Okay. So this is this is just to keep everybody in the same page. So this is how a modern seismic survey is done. There's a boat with lots of cables in the background, and it is recording the seismic data. And here it is how it looks. So normally we have 3D data sets with some description of the subsurface. Okay. The way I was taught about oil exploration was that we are looking for traps, oil traps or gas traps. So we're looking for specific structures which can trap the oil. So the idea is that the oil is somehow transported from somewhere else, and it is accumulated in some traps. And the traps are normally sand layers, they are high porosity, and there is something that needs to seal the reservoir, so the oil or the gas doesn't run away. And there are some layers, which are shale layers normally, and they are the source of the oil. This is the way I was taught in school when I was a student, and for many, many years, that's the way we did exploration. So we were looking for these sand traps, which are often clearly structural. So there is clear structure, closed structures that can create these traps. And this was the main R&D and activity for oil and gas exploration. Traps are of different shapes. So sometimes it's a anticline or some closed structure which has to be closed from all directions. It could be around faults. So faults are of high interest to the industry. And here is an example of a seismic data set, complex structures. So these are very, I would say, attractive from the explorationist point of view. There's a lot of structure, lots of fault, lots of folding, lots of opportunities for creating traps. So the main objective of everything that we used to do was to try to create the best picture that we can get from this, and then try to map it from a geological perspective to understand the geometry of the layers and the faultings and the structures that we see in the subsurface. So our main, I would say, interest was in the geometry of the geological object in the subsurface. we invested a lot of effort into creating better data sets. So here is an example of two different seismic procedures of the same data, and of course this is much better picture than this one. And a lot of the research and the effort went into creating better pictures to improve the understanding of the subsurface. If you can see more details, of course, you can drill with much more confidence. So this was the main objective. And then, suddenly, at least for me, it was suddenly, everybody started to talk about unconventional oil and gas. And there was a huge interest in this activity. And there was quite a bit of talk about the fact that it can change the economy of the world, the politics of the world, and a lot of other things like that. So here is a map of these extent of these unconventional oils around the world. And here is a more detailed picture of the distribution of these reservoirs in the United States. And you could see, for example, that it's almost 50% of the United States is covered by these unconventional potential reservoirs. So this is extremely attractive situation. With unconventional, the layers that we're looking at are source layers. They are shale layers. And the techniques that they use for drilling is horizontal drilling. So they actually go down vertically and then they go into the layer horizontally. And then we use a technique called fracking to try to break the formation and extract the oil and the gas. So this is the main technique that is being used. In reality, this is an example of a drilling place where they drill this reservoir. And this is a map view, and you can see the trajectory of all the horizontal wells. So you can see that actually the area is covered very, very densely with horizontal wells. So all this is being drilled, and this is how they actually extract the oil and the gas from this layer. So of course, when you have such a high sampling rate, it is questionable what else do you want to do. I mean, they have a lot of information from drilling these wells. So the value of the seismic data becomes a question mark. Okay, so here I try to summarize the main differences between what we call traditional, conventional oil and gas exploration and the unconventional game. So the conventional is mostly sand reservoirs, while the unconventional is often shale. Now, in this talk, I'm really concentrating on shale oil and gas. There is other categories of unconventionals, which I'm not going to include in this talk. The conventional reservoirs are high porosity and high permeability, so it's easy to extract the oil from the reservoir, while the unconventional have very low porosity, close to zero, and very poor permeability. So it is very, very difficult to extract the oil and the gas from the reservoir. The conventional, as I said already, is concentrated in small areas which are traps, while the unconventional have huge extent, because we're actually discussing a source rock, and we have extremely large sheets of these shale layers that we're looking at. So it's very large reservoirs. With conventional, we are dealing normally with complex structures, because we're looking for traps, so we're looking for some geometrical structure, and seismic imaging for complex structure is a big issue. So for the last, I would say, 30 years, the industry put most of its energy into trying to better image complicated structures. With the unconventional, the structures are normally simple, flat layers, flat horizontal layers. So all this complex imaging is not extremely exciting for this type of activity. For conventional, the drilling is normally expensive because we're looking at more complex and complex situations because we're already drilling for many, many years. So the simple cheap wells only been depleted, and the expense of the drilling becomes higher and higher. Example is what is going on here in the Mediterranean, where the wells are extremely expensive. While the unconventional, the wells are very cheap because they're shallow wells and they drill on land. So they drill lots of wells because it's cheap to drill. With unconventional, they need to use fracking as a technique. So fracking is an inherent part of unconventional oil and gas. And I don't know if you are familiar with this technique. It's in the United States, they talk about it a lot in the news and in the radio. So everyone in the United States knows about fracking. Here, maybe not everyone knows about it. But that's a kind of a procedure that actually try to break the formation and crack it, so the oil and the gas can flow easily. So the fracking only affects the vicinity of the well. So if you go far away from the well, of course, you cannot extract the oil and the gas from a certain distance. So you need to go and drill another well and frack the formation in a lot of places. So this is very much an inherent part of the technique. From a seismic perspective, conventional, we use conventional seismic acquisition, and for unconventional, we use wide azimuth seismic acquisition, and I will discuss it a little bit later. And as I said, the conventional is depleting resources, while the unconventional is new resources. There is huge reservoirs all over the world, so the potential is very large, and of course this is why a lot of oil companies today move completely to unconventional exploration. They completely left the conventional alone and they are going in that direction. So this is very much a future. So it is a great revolution in the industry, I would say, in the oil and gas industry. Conventional, a lot of it, not all of it is marine, but a big percentage of it is marine activity. Unconventional, I think, is completely on land. So again, this is another difference. So the question is about seismic data. The seismic data is my world. This is my expertise, and many geophysicists work with seismic data, and this is what they know. So when all this started, the geophysicists were kind of worried, what can we do? Maybe they don't need us anymore. Maybe they don't need this seismic activity anymore for unconventional. Why is it not needed? Because the wells are very cheap. They drill a lot of wells, so they actually sample the subsurface with actual drilling well enough. We don't need seismic information. Seismic information is useful when you have no wells or a few wells and you need to know what is going on in between the wells. If you have lots of wells, there's no point in shooting seismic data. Also, seismic data takes time until you shoot the data, until you process it. Sometimes it takes many months or even years before you get the picture. By the time that the seismic data is ready for the explorationist, they already drilled all the wells. They already even depleted the reservoir. So they don't want to wait for this type of information. And of course, they don't have structural complexity. So again, the seismic information is not that needed. So where does it become interesting? It becomes interesting when you want to map some parameters of the reservoir layer. And these parameters are the heterogeneity of the layer, because apparently when you're doing these wells, not all the wells are producing on the same level. Some wells are producing very well, and some wells are producing very poorly. So the mapping of the layer heterogeneity can improve their success rate, improve their drilling techniques and so on. So this is one thing that they would like to know. A certain thing that you can get from the seismic data is the analysis of the brittleness of the layer. And brittleness is a very important parameter because you want to frack the layer. So if it is ductile, it will not frack. So the brittleness is a very interesting parameter. And in fact, the brittleness also may be a function of direction. So it may be easy to frack the layer in one direction and very difficult to frack it in a different direction. So they would like to know this information. And they also would like to have understanding of the stress and fracture regimes. Fractures because the fracking is trying to open natural fractures. So they would like to know what is the direction of the fractures and how many fractures are there. That's one thing. And the stress direction, again, is very, very important in understanding or trying to predict the fracking activity. So these are the things that seismic data can provide to the unconventional oil and gas exploration. So for those of you that are familiar with seismic data and this type of activity, you can sense that this is very, very different from what normally we use seismic data for. Because normally we use seismic data for we look at the cross sections and we try to understand the geometries, the faulting and so on. And here, what we're trying to do, we're trying to understand the behavior of a specific layer that we're looking at. So really mapping the layer properties for this particular reservoir is the objective of the seismic exploration for unconventional oil and gas. Now, to do that, we need what we call wide azimuth seismic data. And maybe I will discuss a little bit later what it means, but it's not the conventional way that seismic data is being required. So this is a picture, it's not a great picture, but it's just an example of what such layer could look like. Normally it's fractured, and normally it's fractured in a very specific direction. And trying to understand the direction of the fracturing is one of the main activities that we do. And you can understand that the seismic wavelength is very large. The seismic wavelengths could be meters, many meters. So it's much larger from the scale of these fractures. So it's not that we can actually map the individual fractures. We still want to be able to say something useful using the seismic data and the long wavelengths of the seismic data. So basically we're talking about average properties that we can extract from this data. But the objective, as I said, is to actually create a pseudo picture like that, which is a seismic picture that describes the distribution of the fractures, stresses, and so on within this layer. Okay. I have an example from the Eagle Ford Shale. Eagle Ford Shale is one of the famous shale reservoirs in the United States, in the south of Texas. And we have a part of this data set. And you can see here the map of the extent of this layer. And a better map, so you can see it extends maybe 20 or 30% of the whole Texas is the extent of this layer. And so this is a depth map. You can see how it is getting deeper to the south. We have a thickness map that shows the layer thickness distribution. And this is the oil gas distribution. So this is oil, this is wet gas, and this is dry gas. This is what they expect. So of course, a lot of companies are exploring this particular layer, trying to learn a lot of things about this particular shale. So one of the things that we can see now, activities that I see in universities and in research institutes, is a lot of activity related to shales. In the past, the shales were something that nobody wanted to study. So everybody concentrated on the sands, and there was a great deal of knowledge about the behavior of sands and its rock properties, its rock physics, and so on. With shale is quite unknown, and so now I can say that most of the R&D activities in the universities is related to shales, trying to catch up our understanding of how these shales behave, what are the properties, and one of the interesting things that we would like to understand is how these rock properties relate to the elastic properties of the layers, so that we will be able to invert from the seismic data and better map the variety of rock properties of these shales. So again, the theory is now just being in its infancy. So there is not enough knowledge about the behavior of these shales. Okay, so here is a seismic section from the Eagle Ford Shale. So it's kind of a seismic section that normally nobody shows you something like that because it's very uninteresting. It's flat layers, so if this was a conventional reservoir, there'd probably be nothing here. But this is the Eagle Ford Shale. So this is the kind of reservoir that we're talking about, and you can imagine that it extends very large distances. So what we want to do is we try to say something about this. We want to be able to say something about the heterogeneity of this layer with a number of parameters, and especially we would like to understand the stress fracture regime. So this is my depth map of this layer. You can see that it's very flat. And this is one of our final maps. So this is Azimuthal Anisotropy, and you could see heterogeneity.
What is the value?
Sorry?
What is the value? Is it velocity, shear wave, the P wave?
No, this is the value here. The two values. The arrows shows the fracture orientation and stress orientation, and the value of this particular map is the difference between the velocity in the two different directions. So it's anisotropy parameter.
But is it P wave or?
P wave.
Okay.
Yes, maybe. Here is another representation of this similar information. The color represents the effect of, I would say, anisotropy. I will explain it in what it means. And in the background, we could see some structural information. This is using an attribute called curvature. So it's some kind of a way to represent the seismic data. Again, we're looking at this layer, so we're not looking at the whole seismic data. We're just extracting, this particular layer. And this is another data set. And just give you an idea of how these things look. It's just a map with lots of heterogeneity. And the arrows tell us something about the fracture orientation. So we can see how here it's oriented in this direction, here it's oriented in this direction. So this is the kind of things that we're trying to get in the seismic data. One of the things that I will emphasize, so this is what I'm giving you here is kind of an overview, then I will go into some details of the kind of research that I'm specifically doing, which maybe is of less interest to you, but one of the main problems that we are dealing with is that it's very difficult to get reliable information from this data. So we have a lot of issues with reliability. So here is, for example, an example of two maps created exactly from the same data, and you could see that they are very, very different. So again, the question is, of course, which one is the right one and which one is not the right one. So this is where we put most of the effort, is trying to estimate the reliability of the measurements that we are providing. Okay. So first, in order to continue, I need to say something about Azimuthal Anisotropy. So the model that we have in mind that we're trying to map is this fracture model. And so it was represented by these slates. And in this fracture model, if you imagine that this is say a set of cards, then the velocity of the sound wave in this direction is different than the velocity in that direction. This direction you can squeeze the layers easily, so the velocity will be slower, while in this direction it will be very stiff, so the velocity will be. And this is the seismic expression of this type of geological phenomenon. So this is the azimuth, the direction in which these layers are oriented. We call azimuth. This is and if we look at a similar formation with much more fractures, the degree of anisotropy will be larger. At least we imagine it this way. So the more fracturing, the more difference will be between the fast velocity and the slow velocity. And you can imagine that this is not fractures, but these are stress directions, because we do expect that there will be differential stress within this layer, and the differential stress, again, is very, very important for the fracking procedure. So we would like to be able to understand the differential stress. The phenomena, or the effect of it on the seismic data is very similar. And still, again, I would say, still being studied. So there is not a clear, I would say, agreement between the researchers about exactly what is the effect of the stress, effect of the structure. Is it exactly the same, or is it similar? So these are still interesting question marks.
This makes the assumption that all the fractures are all in one orientation. You may have many places where the layers has undergone different stress regimes, so you may have different directions, in which case I can't see how the density, how the anisotropy will tell you more about the density of fractures. How can you differentiate between one case and the other?
You're right, that this is just a conceptual model, and the reality is much more complex than that. But the theory is based on this theoretical model. If the subsurface doesn't fit this theoretical model, then of course you're not going to get a good estimation. And so the assumption is that the change, the lateral change, is not that I would say small wavelengths. If the lateral change in the regimes between the fracture orientation is of a larger wavelength, then of course you can map it. But if you know every meter or so you have something else, then the seismic data will see it probably as homogeneous. There's many complexities here. There is a possibility of many places we have perpendicular fracturing. So it kind of cancels, it can cancel the anisotropy completely, or you could have some residual anisotropy if the fracturing in one direction is not completely canceling the fractures in the other direction. So there is a lot of issues here. It's true, it's not a simple, but we are here for the sake of this discussion dealing with a simple model and with the theoretical aspect of it. So I use this ball to try to explain the difference between isotropic and anisotropic wave propagation. So as I discussed, if we have an anisotropy, and it's not a regular, I would say, any anisotropy. It's what we call Azimuthal Anisotropy. So we expect vertical fracturing. We have anisotropy, and the term that we use is the HTI, horizontal transverse isotropy. This is the common terminology. Normally, when people refer to anisotropy in the subsurface related to seismic data, they refer to layering, because shale is highly laminated, so it is anisotropic, but in the vertical direction. So it has symmetrical azimuthal symmetry. And this is a different type of phenomenon that I'm not discussing here. So the topic of this discussion is what we call Azimuthal Anisotropy. It means that the wave propagate in this direction different to the way that they propagate in the other direction. So in the isotropic case, the wave propagation is circular. The wave fronts are circular. And when you have anisotropic HTI, then the wave fronts are elliptic. This is an ellipse. So this is the main difference. And if we are able to create seismic data, which is a function of the azimuth, so if we look at a certain subsurface location from different directions, and we will measure the velocity, change in velocity, we will see an oscillation from 0 to 360 degrees. So this is the kind of effect that we are looking for in the data. We're looking for velocity change. In addition to velocity change, we also look at changes in the amplitude distribution of the seismic waves as a function of the azimuth. So these are the two phenomena that are related to seismic wave propagation that we can detect using seismic data. So this is the kind of thing that we're looking for. So again, my picture here of seismic acquisition. So this acquisition may not be sufficient to collect the data that we need in order to do this type of work. So today, again, because the unconventional plays a big role in the whole story, a lot of experiments are being done with the new acquisition techniques in order to be able to collect wide azimuth seismic data in an effective and efficient way. Now, most of the activity is not on marine, it's on land. Land data is often wide azimuth. What does it mean, wide azimuth? It means that for each surface point, we want to be able to have a source and the receiver in this direction, and a source and receiver in this direction, and a source and receiver in this direction, and for every offset. Okay, so for the small distances and for the wide distances. It means that we need to collect much more data, much more dense, and that we can see the nice distribution of the data laterally. And if we have such ideal situations, then the story becomes very pragmatic, very doable. It was mentioned that I work for Paradigm. Paradigm is a company that develops software for the oil and gas exploration, and we are leading some of these activities. So what I'm going to try to tell you a little bit here is about what we do compared to what other people in the industry are doing. Because we are promoting, I would say, more advanced techniques. The way that the industry is dealing with this challenge is using what they call azimuth sectors. They take this wide azimuth data and they divide it into a number of azimuth sectors. And they process the seismic data independently for each of these sectors. So they process this data that falls roughly in this direction, and they divide it into 3, 4 sectors. Process each data independently, and then bring it all together and try to see what is the differences between the different directions. The difference in velocity and the difference in amplitude. So this is the kind of work that is being done. In Paradigm, we have this technique to create what we call 3D gathers, which contains continuous azimuth information in any granularities that we want to do. So the first question that I have is, does everybody knows what a gather is? Nobody knows what a gather is? Okay, nobody knows what a gather, seismic gather? Okay. So a seismic gather is a set of seismic data that actually comes from one single subsurface point. Okay, so it actually is looking at one subsurface point, but from a variety of angles. And this is a very, very basic entity in seismic data exploration. We are not looking just at the seismic trace at one place, but we actually try to look at it from many angles. And we know that this information, which is a function of this reflection angle, gives us information about the seismic velocity and can also give us information of the rock properties, because the change of the amplitude as a function of this reflection angle is directly related to the changes in the rock properties, especially the fluid content, if it's water, if it's oil, if it's gas. All this is embedded into this process. Now, when we work with the unconventional exploration, the gathers that we are producing are 3D gathers. So they are looking at one subsurface point from all angles and from all directions. So it becomes like a 3D-dimensional volume, which is associated with one point in the subsurface. So this is really the main thing that we have developed in Paradigm. And I have here an example, which is the synthetic example, just to illustrate this phenomena. So you can imagine this is seismic data. It is all associated with one point in the subsurface. So we have lots and lots and lots of these. And if we look into this 3D data, you can see that I have a number of layers here. The change, which we see here, this change is reflecting the velocity of this point. And you can see that the velocity is changing as we are moving the point of view, the direction that we're looking at. Yeah.
Do you have a slide showing how the data is actually collected in order to get this 3D volume?
No, I don't have a slide.
Can you describe it or draw it on the whiteboard?
I can describe it, but in general, standard land acquisition would put receiver lines. We put receiver lines like this and be shooting inside this grid. So to be shots and receivers. So let's say if we select this point that we're looking at, you will have, say, a receiver here and a shot here. You will have a receiver here and a shot here that is reflecting the data, and so on. So each surface point will be covered by shot and receiver pairs from a variety of directions. Now, to get a good coverage requires a lot of planning and so on. Inland, this is normally what they do, which is not perfect, but it's pretty good. On land, as I said today, they have a lot of techniques now. They're running in circles, doing all kinds of things. They're shooting with number of boats. They have number of boats, so they can shoot in different directions. It's a whole science to get to the situation that at each subsurface point you will have a collection of data which will actually be covering all the directions. Now, the Azimuthal Anisotropy, the way it expresses itself in the velocity, in the change in velocity, is with an ellipse. So actually, when we look at the data and we look at the curvature of these events, we can fit an ellipse to this data. And the ellipse will tell us, first of all, the difference between this axis and this axis will tell us the intensity of the anisotropy. And we expect that the intensity of the anisotropy is directly related to fracture density or to stress intensity. And the orientation of this ellipse in the space will give us the fracture orientation. So actually we do this analysis point by point, and then we put it on a map, and we can see how it is distributed. So it sounds easy, it's not so easy, but it's doable. Another phenomena that have been again discovered, or I would say analyzed quite recently, is the changes in what we call AVO. Anybody knows what is AVO? Okay. So let's assume that you know the changes in the AVO as a function of the orientation, the direction, the azimuth. So this is a theoretical curve that is showing you, for example, in this particular case that is being analyzed here, for azimuth 0, this would be the AVO. So this is angle or offset, and this is the amplitude of the seismic response. And you can see that it is increasing like that with the angle, and if you go to 90 degrees, you will see completely different response. So this is another phenomena that we use in order to map this anisotropy phenomena on the horizon. Now, these two phenomena are supposed to actually give you the same answer, although they are quite independent in what they do, but we can imagine that the velocity is a long wavelength parameter, because the waves are propagating, and in order to see the effect of the velocity, we have to wait a long time. So it's actually averaging a lot of information within the layer. While the AVO, for those of you who know what it is a function of the reflection at the subsurface. So it's much more local phenomena. So we could say that it actually gives us a better description of the point phenomena. So we do expect that not necessarily these two measurements will give us exactly the same answers. And again, one of the things that people are still trying to learn is how to integrate these two pieces of information to one consistent picture. So this is one of the challenges. So one of the things that you could see is that there is a lot of questions in this. This is a science in its infancy, and for students, it's a great opportunity. Okay, so this is an example of how does the AVA or AVO as a function of angle changes with azimuth. So again, we're looking at this 3D gather, it's a synthetic gather. So the AVA is actually, what you see here is the intensity, the change of the amplitude as we go further away. So the distance here is the distance, the offset, or the distance between the source and the receiver. And you can see that it is changing as this circle is rotating. So this change is the phenomena that we are trying to measure in our display. discussions. Okay, so when we slice this, just put a slice here. So this is the amplitude of the seismic wave. We can see again that it is ellipse. So the whole science, the mathematics is the mathematics of ellipses. And actually we're trying to fit an elliptic curve to the data in order to try to understand what is the azimuth, the orientation, and what is the intensity of this particular phenomenon. I'm going to jump a little bit and show you some few examples of data. So this is the gather, the real gather from the Eagle Ford shale. This is axis is reflection angle. This is depth, and this is the event. So it's actually increasing offset. You can imagine that it's increasing social signal offset. And inside it, we have azimuth oscillating. So we have 1 to 360 for this angle, then for this angle, and so on and so on. And as we go further to this side, we start, as the long fingers, we start to see these oscillations. These oscillations are actually what I showed you in the previous picture, is this effect of the azimuthal variation in the velocity which we are detecting. This is exactly the same gather displayed in a different way. And here, this axis is the azimuth. So this is 0 degrees, and this is 360 degrees over there. And all these traces are organized somehow inside this kind of spread inside. And you can see that it's quite messy. Now we have this automatic procedure which is trying to, what we call, flatten this, make it flat. And by making it flat, we can detect what is the function that we need in order to flatten it. And this function gives us the information that we want, which is the velocity variations as a function of azimuth and the orientation. And I'm going to skip this. Okay, so this is my gather. And this is the gather after it was flattened. So you see there is some function in there that makes everything go in the right place. And it is using an ellipse for the velocity. Still, when we look at it, we can see with our own eyes some interesting parameters. We can see that this here is a little bit higher, and it goes lower, and then it becomes higher, which means that we can see with our own eyes this azimuthal oscillation. So, of course, if we can see it with our eyes, we can have a computer program that can detect it very easily. We also can see that the amplitude of the events have some kind of a high here and a high here, which is consistent with the velocity height. So this is our AVO phenomena. You can see that it's not very easy, it's not very smooth, it's not really circular, so there is a lot of reliability issues there. One of the main issues for reliability is the fact that actually in the technique itself, we're trying to fit these ellipses to the data. And as long as the data is good and it's very elliptic, everything is great. But because we're mapping heterogeneity, and some areas are more anisotropic and some regions are less anisotropic, and some of them are totally isotropic, then we need to be able to differentiate between these. Why? Because when we're trying to fit an ellipse to a point which is isotropic, the ellipse is a circle. And when you have a circle, you cannot determine the orientation. So the orientation becomes what we call unstable, and a lot of a lot of these analyses fall because of this, because they're trying to create an answer everywhere. So a lot of these things that we do is trying to actually map the reliability of the analysis as part of this discussion. I think I'm going to stop here and
Okay, thank you
get
very
questions.
much. Any questions, please? Yeah.
So, two questions. First one, it seems that you're basically assuming that your sediment has no inherent anisotropic related to the internal structure of the sediment, or the sedimentary bedding. Am I understanding it correctly? And if you do assume it, how do you tease it out from your general anisotropy? The other issue is your case. I don't know the Eagle Ford, but looking at units we know from around here, they have multi-directional joining system. Some of them are bed limited, some of them are non-bed limited, and those have internal rotation of stress field during time. So how do you, and those would result in an average vector that is unnecessarily representative of the actual directionality of the joint system as it would be reflected in the anisotropy.
Okay, these are good questions. They are more of the same. So as I said, this is a very generalized and simplified analysis. So related to bedding, you know, if the layer is flat and there is bedding, then it is isotropic from the azimuthal.
I'm not talking about the anisotropy of the bedding itself. I'm talking about the directionality of the grains.
Of the what?
The grains themselves.
The directionality of the grains themselves that are, well, yeah, what we measure is a total field. So if you have some intrinsic anisotropy, which has some reflection on azimuth, then of course you will not be able to separate it from the fractures. So when I say fractures, it's just really a figure of speech. And as I said, we don't really know what we are measuring. We are measuring anisotropy, and then the question is how to interpret it. But we know that the fractures and the stress have similar effect from the drilling and fracking perspective. So normally they are not so insistent on, please tell me if it's fractures or stress. First of all, they know, because they are familiar with the layers and they know what they're looking for. But the effect that they have on the fracking of is mainly, I would say, mainly on the stress field. And we are giving them very generalized information. So it's not a 100% decoupling of all parameters. But this is only one phenomenon that you're saying. If you have a little bit of a structure, so even if you have conventional bedding, it has a azimuthal perspective, which is included into this process. So the model that I described here, which we call HTI or HTI anisotropy, horizontal transverse isotropy, is a very simple model. Normal models are much more complex, and we're dealing today with what we call orthorhombic models, which have much more complex fracturing system. But these models are more difficult from the point of view that they have more parameters to describe this phenomenon, or describe the symmetry of the phenomenon. And the more parameters you have, the less reliable becomes your analysis. So, as I said, this is a science in infancy, and so this is where we are today. I think this is where the industry is today. Some attempts, mainly theoretical at this point, to go for more complicated models, to try to understand more complex models. What I didn't describe, and maybe it's interesting for you, is the brittleness analysis, because some of these parameters that we use, we extract elastic parameters of the layers by forms of inversion. So we can say something about Young modulus and Poisson's ratio. The relationship between Young modulus and Poisson's ratio is directly proportional to brittleness. So this is another parameter that the engineers are very interested in. and I would say would be one of the main reasons why they would go and do such an analysis. And again, it is also anisotropic. So brittleness is also anisotropic. So a layer can be brittle in one direction and ductile in another direction. So they are looking for the best orientation. They want to put the well in exactly the optimal orientation. That's really the main objective.
Okay, I think that you have time for one very short question, probably, and then we can ask Anat later.
I'm good.
Okay. Your question?
You said that you rely in fracking on the simplicity of the structures. That's probably makes it much more economical. How do you know that the structure is simple without a seismic survey?
Well, first of all, in the United States there is no such thing, no seismic survey. You know, even in Israel, I think the seismic service almost everywhere. They know the layers very well. They know how. They don't rely on the seismic data, or they don't necessarily rely on the seismic data on the details of the structure. Overall, they know that it's horizontal and it's flat. They understand the geology. They know what's the story there. When they're drilling, with horizontal drilling, they have a lot of techniques to actually make sure that they are following the layer, so they can go up and down to fit into the layer. But they don't feel that they need to map the details of it necessarily in advance, because overall it's simple and they don't really care so much about the faulting, and they don't have to really place the fault in exactly the same place. So,
Okay, thank you.
thank you.
Okay.